CSC159. Computer Organization. Chapter 5, Interfacing and Communication. Prepared by Sidi Fatima Noor Abwahab. Chapter 5. Part 2, I/O Techniques. Programmed I/O. Interrupt-driven I/O. Direct Memory Access, DMA. Programmed I/O versus interrupt-driven I/O versus DMA. I/O Techniques. I/O Techniques. Programmed I/O. CPU-controlled I/O. I/O occurs under the direct and continuous control of the program requesting the I/O operation. Interrupt-driven I/O. External input controls. A program issues an I/O command and then continues to execute, until it is interrupted by the I/O hardware to signal the end of the I/O operation. Direct memory access controllers. Method for transferring data between main memory and a device that bypasses the CPU. A specialized I/O processor takes over control of an I/O operation to move a large block of data. Programmed I/O. Programmed I/O. Simplest method for performing I/O where an I/O module is connected to a pair of I/O registers in the CPU via a bus. I/O data and address registers in CPU. One word transfer per I/O instruction. Address information for each I/O device. Programmed I/O is obviously slow, since a full instruction fetch execute cycle must be performed for each and every I/O data word to be transferred. Primary use. Keyboards. Communication with I/O modules, example, the transmission of commands through a network I/O module or modem. With programmed I/O, data are exchanged between the processor and the I/O module. The processor executes a program that gives it direct control of the I/O operation, including sensing device status, sending a read or write command, and transferring the data. When the processor issues a command to the I/O module, it must wait until the I/O operation is completed. If the processor is faster than the I/O module, this is wasteful of processor time. Programmed I/O example. This figure illustrates the concept of programmed I/O. For example, CPU executes input 24 instruction. Address 24 is copied to the I/O address register. Then, address 24 is recognized by the keyboard I/O module. A read-write control line indicates that the instruction is an input. A buffer in the I/O module holds a keystroke, in this case ASCII 68, the letter D. The data is transferred to the I/O data register. From there it is copied to the appropriate accumulator or general purpose register, completing the operation. Interrupt-driven I/O. Interrupt-driven I/O. Interrupts are provided primarily as a way to improve processing efficiency. Peripheral devices may demand the attention of the microprocessor during normal program execution. With interrupt-driven I/O, the processor issues an I/O command, continues to execute other instructions, and is interrupted by the I/O module when the latter has completed its work. What is an interrupt? A call for the microprocessor to interact or service the interrupting unit. An interrupt is a signal or call for the CPU to interact or service the interrupting unit. Interrupt causes the temporary suspension of the program in progress and jump into a special interrupt processing program. Signal that causes the CPU to alter its normal flow on instruction execution. Frees CPU from waiting for events. Provides control for external input. Classes of interrupt. Virtually all computers provide a mechanism by which other modules, I/O, memory, may interrupt the normal processing of the processor. This table lists the most common classes of interrupts. Types of interrupt. There are two types of interrupts. Hardware interrupt. This interrupt is being sent by the peripheral devices to indicate certain conditions such as keyboard entry, printing problem, and power failure. Software interrupt. Modern CPU has a set of instructions to simulate an interrupt, for examples are halt and int. Category of interrupt. Maskable. It can be selectively disabled, interrupt will be ignored. The processor does not recognize a maskable interrupt unless the interrupt enable flag, if, is set. Non-maskable. It cannot be disabled or ignored. The interrupt will always be acknowledged and accepted, such as a power failure. Recognition of such interrupts cannot be prevented. Interrupt lines. It would be desirable to interrupt the normal flow of a program to react or service a special event. Modern computers provide interrupt capability by providing one or more special control lines known as interrupt line to the processor. PC may contain as many as 32 interrupt lines, IRQ0 to IRQ31. IRQ stands for interrupt request. Interrupt services. The message sent through the IRQ line will cause an interrupt. The interrupt will cause the computer to suspend the program being executed and jump to a special interrupt processing program. Interrupt handler program is the action taken by the microprocessor when an interrupt occurs. This is also known as interrupt routine. Servicing the interrupt. There are 4 steps taken by microprocessor to handle an interrupt. The microprocessor finished the current instruction until the end of an instruction cycle. Normal operation is suspended. The microprocessor jumps to the location in memory where the interrupt service routine has been stored and executes the routines. When the interrupt routines complete, it would return control to the interrupted program. Servicing an interrupt. Since the computer is capable only of executing programs, interrupt actions take the form of special programs, executed whenever triggered by an interrupt signal. Interrupt procedures follow the form shown in this figure. Before interrupt arrives, program is executing. The program counter points to the current instruction. When the interrupt is received by the CPU, the current instruction is completed. All the registers are saved in the stack area, or in a special area known as a process control block. The PC is loaded with the starting location of program B, the interrupt handler program. This causes a jump to program B, which becomes the executing program. When the interrupt routine is complete, the registers are restored, including the program counter, and the original program resumes exactly where it left off. Multiple interrupts. There are many different types of input and output devices and event indicators connected to the interrupt lines. Multiple interrupts can occur from time to time. 2 different processing methods used to determine which devices initiated the interrupt are vectored interrupt and polling. Vectored interrupt. Vectored interrupt is a processing technique in which the interrupting device directs the processor to the appropriate interrupt service routine. A word known as a vector is placed on the data lines. Processor uses the vector as a pointer to the appropriate device service routine. This word is referred to as a vector and is either the address of the I/O module or some other unique identifier. The address of the interrupting devices is included as part of the interrupt. The vectored interrupt is faster than polling but requires additional hardware to implement. Vectored interrupt processing versus polled interrupt processing. Some computers use a method known as vectored interrupt, in which the address of the interrupting device is included as part of the interrupt. Another method provides a general interrupt that is shared by all devices. The computer identifies the interrupting device by polling each device. These two methods are illustrated in above figures, respectively. Polling. Definition. Technique or approach to taking care of peripheral devices by checking each device in rotation at frequent intervals to see if it needs service. Provides a general interrupt that is shared by all devices. Computer identifies the interrupting device by polling each device. Disadvantages. The computer time spent in polling is largely wasted. Not efficient when the processor needs to perform other tasks or multiple tasks. Polling process. Microprocessor would do routine checkup for the peripheral devices to see if it needs service. A better system is an interrupt process where it allows the processor to continue normal sequential execution until there is especially needed attention. Handling multiple interrupts. Can be handled by assigning priorities to each interrupt. A higher priority interrupt will be allowed to interrupt a lower priority interrupt. Lower priority interrupt will have to wait until a higher interrupt is completed. Establishing priority. Most computer system allows the system manager to establish priorities for various interrupt. The three methods to establish priorities. Logical way, time-sensitive situation has a high priority. Hardware, physical location of the devices. Software, assigning a priority number to each interrupts. Servicing multiple interrupts. This figure shows a simple usage of interrupt. Servicing multiple interrupts. This figure shows a simple example of this situation. In this figure, interrupt routine C is the highest priority, followed by B and A. Usage of interrupt. The way which an interrupt is used depend on the nature of the devices. There are several ways in which interrupt are used. As an external event notifier. As a completion signal. As a means of allocating CPU time. As an abnormal event indicator. External event notifier. This frees the CPU from the necessity of performing polling to determine that input data is waiting. Indicates that some external devices require action. An example is keyboard input. Example, keyboard input. Suppose a key is struck on the keyboard. This causes an interrupt to occur. The current program is suspended, and control is transferred to the keyboard interrupt handler program. The keyboard interrupt handler first inputs the character, using programmed I/O, and determines what character has been received. It would next determine if the input is one that requires special action. If so, it would perform the required action, for example, suspending the program or freezing the data on the screen. Otherwise, it would pass the input data to the program expecting input from that keyboard. Normally, the input character would be stored in a known memory location, ready for the program to use when it is reactivated. When the action is complete, that is, when the interrupt has been serviced, the computer normally restores the register values and returns control to the suspended program, unless the interrupt request specifies a different course of action. Completion signal. To control the flow of data to an output device. Interrupt serves to notify the computer completion of a particular course of action. An example is printing process and DMA process. Example, a print handler interrupt. As noted previously, printer is a slow output device. The computer is capable of outputting data to the printer much faster than the printer can handle it. The interrupt can be used to control the flow of data to the printer in an efficient way. The computer sends one block of data at a time to the printer. The size of the block depends on the type of printer and the amount of memory installed in the printer. When the printer is ready to accept more data, it sends an interrupt to the computer. This interrupt indicates that the printer has completed printing the material previously received and is ready for more. Allocating CPU times. Is used as a method of allocating CPU time to different programs or threads that are sharing the CPU. The computer system provides an internal clock that sends an interrupt periodically to the CPU. Once the CPU receives the interrupt, it will suspend the current program and go to the next program to be executed. Example, using an interrupt for time sharing. Since the CPU can only execute one sequence of instructions at a time, the ability to time share multiple programs or threads implies that the computer system must share the CPU by allocating small segments of time to each program or thread, in rapid rotation among them. Each program sequence is allowed to execute some instructions. After a certain period of time, that sequence is interrupted and relinquishes control to a dispatcher program within the operating system that allocates the next block of time to another sequence. This is illustrated in this figure. Abnormal event indicator. Used to handle abnormal events that affect the operation of the computer. The events are directly at the problems within the computer system itself. An example is execution of an illegal instruction such as division by zero, non-existent code, and hardware errors such as power failure. Internal interrupts are sometimes called traps or exceptions. Direct memory access, DMA. Direct memory access, DMA. Method of transferring data from the computer's RAM to another part of the computer without processing it using the CPU. While most data that is input or output from your computer is processed by the CPU, some data does not require processing, or can be processed by another device. DMA can save processing time and is a more efficient way to move data from the computer's memory to other devices. Required conditions for DMA. The I/O interface and memory must be connected. There must be a method to connect together the I/O interface and memory. In some systems both are already connected to the same bus, so this requirement is easily met. In other cases, the design must contain provisions for interconnecting the two. The I/O module must be capable of reading and writing to memory. It does so by simulating the CPU's interface with memory. Conflicts between the CPU and the I/O module must be avoided. This requirement simply means that memory can only be used by one device at a time. Interrupt is required for completion. Examples. A sound card may need to access data stored in the computer's RAM, but since it can process the data itself, it may use DMA to bypass the CPU. Video cards that support DMA can also access the system memory and process graphics without needing the CPU. DMA Instructions. Application program requests I/O service from operating system. Privileged programmed I/O instructions. To initiate DMA, programmed I/O is used to send the following information. Location of data on I/O device. The starting location in memory. The size of the block. Read or write. Interrupt to CPU upon completion of DMA. When the transfer is complete, the DMA module sends an interrupt signal to the processor. Thus, the processor is involved only at the beginning and end of the transfer. CPU sets up a device such as a disk drive for DMA transfer, and disables DMA interrupts. Data is transferred into DMA memory, while the CPU is freed to handle other tasks. Once the data transfer is completed, the CPU is interrupted to allow it to handle cleanup after the DMA transfer. Programmed I/O versus interrupt-driven I/O versus DMA. Figure A gives an example of the use of programmed I/O to read in a block of data from a peripheral device, example, a record from tape, into memory. Data are read in one word, example, 16 bits, at a time. For each word that is read in, the processor must remain in a status checking cycle until it determines that the word is available in the I/O module's data register. This flowchart highlights the main disadvantage of this technique. It is a time-consuming process that keeps the processor busy needlessly. Figure B shows the use of interrupt I/O for reading in a block of data. Compare this with figure A. Interrupt I/O is more efficient than programmed I/O because it eliminates needless waiting. However, interrupt I/O still consumes a lot of processor time, because every word of data that goes from memory to I/O module or from I/O module to memory must pass through the processor. Figure C shows the use of DMA. When the processor wishes to read or write a block of data, it issues a command to the DMA module. The processor then continues with other work. It has delegated this I/O operation to the DMA module. The DMA module transfers the entire block of data, one word at a time, directly to or from memory, without going through the processor. When the transfer is complete, the DMA module sends an interrupt signal to the processor. Thus, the processor is involved only at the beginning and end of the transfer. References: Computer Organization and Architecture Designing for Performance, 8th edition, William Stallings, Prentice Hall. The Architecture of Computer Hardware, System Software, and Networking and Information Technology Approach, IRV Englander, John Wiley & Sons Incorporated. Slide number. Thank you everyone. Stay safe. See you next topic.